Good morning, everyone. Today we trying to finish chapter 5, starting section 5.6. Okay, so we'll discuss 5.6, 5.7, 5.9, and 5.10. Okay. First of all, let me share the screen of my iPad with you. Okay. All right. So I hope you can see the screen of lecture notes. So section 5.6 is small sample confidence intervals for the difference between two means. Okay. So chapter 5 is all about confidence interval depending on different situations. In this section, this is small sample for the difference between two means. Okay. So if we define x1, x2, and xnx is a random sample with the size of nx from a normal population. Okay, so this is the requirement has to be follow a normal distribution with the mean value of mu x and the standard deviation of sigma x. Okay. And y1, y2 to y is another random sample with size ny, also follow a normal distribution. So that is condition requirement with mean value of mu x and the standard deviation of sigma y. Okay. And also we need to assume these two samples, x and y, are independent. If that's the case, if the two population does not have the same variance, that means sigma x and sigma y is not equal. Okay. And then we can calculate for any level of confidence interval, okay, for the difference between these two means, mu x minus mu y. All right. So which is this range. So this is sample mean for x minus sample mean for y. Okay. And here Sx is the sample standard deviation for x, sample standard deviation for y, and x is the sample size for x, and y is sample size for y. Okay. And here is the t-value, okay, from the table 8.3 students t distribution. So the v here is the degree of freedom. Okay, that's the equation for v. Okay, which is here. So the equation looks complicated, but that's a function of sample standard deviation, sample size. So we just simply plug a number and we calculate degree of freedom, which is here. Remember, for students t distribution, one of the parameter is degree of freedom. And then another one is half alpha here, which is depending on what level of confidence interval we want. Okay, so let's look at one example. So here we have reason-based composite are used in restorative dentistry. Okay, one of the articles present a comparison of the surface hardness of specimen cured for 40 seconds, okay, with constant power with that the specimen cured for 40 seconds with potentially increasing power. Okay, 15 specimens were cured in each method. Okay, those cured with constant power had average surface hardness of 409.9, standard deviation of 10.6. those cued with exponentially increasing power had another average service hardness of 367.2 with standard deviation of 6.1. Okay, so we have two sets of value with the mean value and the standard deviation told us. The question is asking for 98% confidence interval for the difference in the means. All right, so confidence interval for the difference between two means. Okay, so that tells us we're going to use the equation in section 5.6. All right, so let's do it together. Okay, so the sample mean for x is equal to 409. Okay, and the sample standard deviation Sx is 10.6. Question tells us the sample size Nx is 15. Okay, so similarly for another sample y, the mean is 367.2. Okay, sample standard deviation Sy is 6.1, and the sample size Ny is equal to 15 also. All right. So first of all, we need to calculate the t value. Right. As you can see from here, we need to calculate the t value. Okay. To get the t value, we need to calculate the degree of freedom v, which based on this equation. Okay. So based on the equation for degree of freedom, okay, we plug in the sample standard deviation of x, nx, sample size. So we calculate the v, which is around 22. Okay, so we can calculate the t value. So t 22 for the degree of freedom based on 98% confidence interval. Okay, so we can calculate alpha. So 98% equal to 100 times 1 minus alpha. Okay, so from there we get alpha equal to 0.02. So half alpha will be 0.01. Okay, so this is half alpha. Okay, so based on table 8.3, all right. See the table 8.3. All right. So based on table 8.3, the value will be 2.508. Okay. I will try to get table 8.3 for us. I think it's somewhere. Sorry. Here. All right. Okay. For the degree of freedom of 22, which is here, so 22, and half alpha is 0.01. Okay. So we get 2.508 here. 2.508. Okay, let's go back. Okay, so that's how we get 2.508 here. So then we can calculate a 98% confidence interval is equal to, based on the equation in the previous slides, the mean value of x minus the mean value of y plus minus the t-value, which is 2.508, and the square root of sx squared over sample size nx plus sample standard deviation as y squared over ny. Okay, so all this value is here. Okay, for example, sample mean for x is 409. So we plug in this number, we can calculate this 98% confidence interval. Okay, so I will just skip the details. So let's continue. So the above example consider the two population has different variance. Okay, this is the general case, but if the two population has the same variance, we have another simplified equation showed here. Okay, so again, for any type of confidence interval, if they have the equal variance, we use this equation. Again, we use student's t-distribution, but here the degree of freedom is nx plus ny minus 2. Okay, and this is same half alpha. SP is called pooled standard deviation, which is based on the sample size and sample standard deviation. Okay, so plug in the number, we calculate the SP, and then we plug the value of SP in this equation. Okay, so same idea. And here shows another example, example 13. So machine is used to fill plastic bottles with bleach. Okay, one sample has 18 bottles. The sample size is 18, has a mean value of 2.007, standard deviation of this. All right, and then you move to another location. We have another sample of 10 bottles with another mean and another standard deviation. Okay. Assume both bottles come from approximately normal population, and is that it is unlikely to change the standard deviation, which means for these two samples, we can assume they have the same standard deviation, asking for 99% confidence interval. Okay, so because they have the equal standard deviation, so equal variance, so we use this equation instead. Okay. All right. So, all right, so let's do it together. Again, the sample mean for x is 2.007, sample standard deviation 0.01, sample size 18. Okay, so for y, the mean value 2.001, sample standard deviation for y, sample size for y. Okay, and because they have the same sigma, okay, so the same variance, so we use the previous slide's equation. So SP equal to here. Okay, use this equation, plug in the number nx, sx, and y as y. Okay, so SP is equal to 0.0107. Okay, and then for the degree of freedom, because we need the students, the t value, okay, so for the t value, the degree of freedom is nx plus ny minus 2. Okay, this is degree of freedom. And half alpha is the same. Okay. So for the degree of freedom, nx plus ny minus 2, okay, is equal to, 26. Okay, so the t value for 26, half alpha is 0.05. Okay, because for 99% confidence interval, half alpha is 0.05, 0.005. Okay, so use table 8.3 for that t value. So we calculate the t value is equal to 2.779. Okay, so then we can use the equation here to calculate the confidence interval. Okay. All right. So that's the idea. Right. And here it says, do not assume the population variance are equal. Okay. The example we just discussed, they have the same variance. Okay. But do not always assume the population variance are equal. Because even though sometimes the sample standard deviation are similar, but does not necessarily mean the population standard deviation and the variance are also equal. So unless the question tells us for sure the population variance are equal, so we just assume they are not equal. Okay, so we should use the general form equation, this one. Okay, if we are not sure the variance of the two populations are equal. Okay. Okay. Again, the best practice is to assume the variance are unequal unless we are sure they are equal. Okay. So that is section 5.6. Next section 5.7 is confidence intervals with paired delta. Okay, so first of all, what is paired delta? In some situations, we may want to design experiments so that each item in one example is paired with another item. Okay, for example, let's say we have several concrete specimens. Okay, and for each concrete specimen, we measure two different things. So one is the density. The other one is the strength. Okay, So measure density and strength for different samples, 1, 2, 3, 4. Okay, and density and strength are called pair data because for every single sample, we measure its density and its strength. Okay, so this is an example of pair data. And when this is done, the sample are no longer independent because the value of density and strength are associated with a certain sample. So this is what we call pair data. Okay. So here shows another example. A tire manufacturer want to compare the tread wear of tires made of new materials. Okay, so different tires with different materials. Okay, so one tire on each type is placed on each front wheel of each of the 10 front-wheel drive automobile. Okay, the choice as to which type of tires goes on the right wheel and which on the left is made with flip of a coin. Okay, and each car is driven 40,000 miles, and then the tires are removed and depth of tread on each tire is measured. Okay, so this is a pair data because on every automobile, one tire is from the new materials, one tire is from the old materials. Okay, so here shows the tread depths for different cars. So this is one pair data, and here is another pair data. Okay, so these two set of results are not independent because they are associated with the same car. So if x1, y1 is one pair, xn and yn is another pair, okay, and if we define di is the difference between xi and yi, okay, this is one pair data, okay, and the population mean for x and y is mu x and mu y, and we want to find out the confidence interval for the difference between mu x and mu y. Okay. And if we let mu d, which is the mean value of the difference between x and y, represent the population mean of the difference, then mu d will equal to mu x minus mu y. Okay. And that tells us the confidence interval for mu d will also be a confidence interval for mu x and mu y. Correct. So the sample d, which is the difference between the pair data d1 and dn, is a random sample coming from population with the mean value of mu d. Okay. And then we can use this set of equation to calculate the confidence interval. Okay. So d1 to dn is a small random sample. Again, the condition is small of pair data. And another requirement is the population of difference are normal, so follow a normal distribution. Okay. And then we can calculate any confidence interval for the mean value of the difference, use this equation. Okay, so again, we use students' t distribution. The degree of freedom is n minus 1, and this is half alpha. Okay, and this SD is standard deviation of the sample. This is n is the sample size. Okay. If the sample size is large, we're going to use another equation. Okay, if sample size is large, then we can use the z value. Okay, this is the table upon 2 instead of t table, which is table upon 3. Okay, and sigma d mean is mean value of d. Sometime if we do not know that, we can use sample standard deviation st over square root of sample size n. Okay, so here shows two different situations depending on the sample size, large or small. So here shows another example. Group of 5 individuals. So this is small sample. We should use the first equation here. So small sample, the first equation. Okay. So 5 individuals with high blood pressure were given a new drug that was designed to lower blood pressure. Okay. Systolic blood pressure was measured before and after the treatment. So this is before, this is after. So this is the 5 patient. So this is paradigm. Question asking for 90% confidence interval for the mean reduction in systolic blood pressure. Okay, so reduction means the difference between before and after. Okay, all right. So first of all, we can calculate the mean value of the difference. Okay, the mean value of the difference is just add all these values together and divide by 5 easily. So that is 31.4. Okay. And also we can calculate the sample standard deviation based on the equation from previous chapter, chapter 2. Right. So sample size n is 5, xi is this. Okay. And this is sample mean. Sorry. Okay. So nx here. Okay. So nx here is 31.4. Okay. And n is 5. Xi is just 25, 32, 39, 23, and 38. Okay. So from there, we can calculate SD, which is 7.30. Okay. So the t value, n minus 1, half alpha, okay, is equal to t4, okay, because n is equal to 5, so the degree of freedom is 4. Okay. 90% confidence interval, so half alpha is 0.05. Okay, so from there, use table 8.3, the t value is 2.132. Okay. So 90% confidence interval will equal to mean value of t plus minus tn minus 1 of alpha. Okay. The mean value of t is 31.4. The t value is 2.132. SD is 7.3 here. Okay. So the sample size is 5. Okay, so from there we can calculate the confidence interval.